Welcome to example number 12. Normally we go over this kind of problem in class and we can discuss it qualitatively together. But in case you missed this, let's go over this and talk about it. I find that students quite often become very good problem solvers solving circuits mathematically, but they fail to think globally in an entire circuit. They have difficulty in seeing how this one component within the circuit affects the current and the voltages throughout the rest of the circuit. So, take a look at these questions, and we're going to go through it one by one. So, first part, how does the total resistance of the circuit change when this switch S has been closed? Take a minute now, think about it, your answer carefully, and jot it down here. If you answered that the total resistance of the circuit decreased, you're correct. Let's talk about that. My first step is probably to redraw this circuit out all horizontally, a before picture and then an afterward picture. So there's the before picture, but the switch is open. So really there's not going to be any current flowing through B, and so this isn't really part of the circuit. So you really have two resistors in parallel and that combination in series with the resistor A. And then when you close the switch, you now have three resistors in parallel when you only had two before. So how does adding another resistor in parallel affect the total resistance of the circuit? And what commonly people make as a mistake is they say that, well, you add more resistors, you get more resistance. That's not true. That's true in a series connection where you add more and more resistors in series. That's going to make your total resistance get bigger. But in a parallel connection, adding more resistance is going to decrease the total resistance. Think of these as like water pipes. Think of our water analogy. Imagine you have water flowing through here and then it diverges into two separate paths, and now it splits into three different paths. As you add more different paths for it to flow through, that is going to provide less resistance to the fluid flow. Or just think of it mathematically. Resistance equals resistivity length all over area. What you're doing is you're increasing the cross-sectional area of the fluid flow. So A is getting bigger. L is staying the same. That's the length of the pipes. That's going to cause a decrease in the total resistance. So whenever you add more and more resistors in parallel, the total resistance decreases. Okay, now do B. How does closing this switch affect the total current that is driven through the battery? Take a moment, write down what you think is the answer. Okay, hopefully you realize that the total current of the circuit, which is the same as the current that goes through A, is going to increase because the total resistance has decreased while keeping the total voltage the same. Remember, Ohm's law says that the EMF, or the voltage, equals the total current times the equivalent resistance. Because the total resistance has decreased, the total net current must increase because the EMF is remaining constant. Now go on to part C. How does the total current through each of these components change? A, B, C, and D. Write down your answers. Okay, let's tackle these one by one now. Now the current through A will increase. Why does that increase? Well, you have to realize that the current through this element is the same as the current that goes through the battery. They're the same current. The current that goes through the battery is the same as the current that goes through resistor A because the resistor is in series with the battery. So whatever happens to the net current is going to be what happens to current A. So current A increases for that reason. And current B. Well, initially there was no current going through here because the switch was open. Now when the switch is closed, then the current must flow through and current B will increase because there is no current and now there's current. Now with C. How do you answer C? A couple ways to look at it. One could say or argue that initially there were only two paths for the water to flow through, so the total current was only being divided into two pieces. And so then when you close and create a third path for this current to flow through here, then now the total current is being divided into third, a third, and a third. And so therefore the current through C and D decreases. But I don't always like that reasoning, because one could say, well, but the total current has gone up too. So doesn't that affect? Well, yes, it does. But dividing into a third is going to be a smaller change, or cause that current to decrease more than the increase from this little bit of current here. Or better yet, you could also argue it by the voltages, which we'll answer in a moment. So to summarize here, I have current A increases because that's the same as the total current, and that's gone up. Current B increases because initially there was no current and now there's current going through. And current C and D decrease because the voltages of C and D decrease. Think of it in terms of Ohm's law. The voltage of C equals the current through C times the resistance of C. And the resistance is remaining constant, and because the voltage across C or D both decrease, then the currents through C or D decrease. Okay, now discuss what happens to the voltages across A, B, C, and D. Take a moment and jot down your answers. Okay, so for A, the voltage of A should increase. Why? Because the resistance stays the same, but the total current through that one has increased. And because voltage is proportional to the current, then an increase in current will cause an increase in voltage. B, well, when the switch was open, there was no voltage, and now when the switch is closed, there is voltage. So that definitely the voltage goes up as well. So A and B, the voltages go up, and C and D, the voltages go down. Let's talk about why they go down for C and D. Imagine if you were to put a voltmeter across A. We'll call that voltage 1 right across here. And then you were to put a voltmeter across the parallel connection of C and D and B. And we'll call that voltage 2. And then we have the EMF of the battery. And hopefully you'll see that the EMF of the battery is equal to the voltage drop across resistor A, which we've labeled as V1, plus the voltage drop across B, C, or D, which is that parallel part, V2. So the sum of these two voltages, V1 and V2, add up to the total EMF of the battery. But the EMF of the battery is remaining constant in this whole scenario. But voltage 1 has increased. Why has it increased? Because the total current through it has increased. And therefore, this leaves a smaller share of that total voltage for the parallel part, which is measured by this voltmeter V2. So voltage 2, which is reading the voltage across C and D, goes down. And that is the reason why voltage C and D goes down. So once again, to summarize, the voltage of A has increased because the current through resistance A has increased. And the same reasoning can be used for B, because there was no current through it initially, so no voltage, and then suddenly there is current going through this branch, and hence there is voltage across that resistor. And then for C and D, the EMF remains constant, which is equal to the sum of the voltage across the first resistor A plus the voltage across this parallel connection from B, C, and D. So we'll call that voltage 2. The total EMF is remaining constant, and the voltage across A has decreased, hence leaving less voltage for the parallel connection C and D. Okay, now to do part E. What happens to the power output of the entire circuit? Plus, I'd like you to tell me what happens to the power individually of all the circuit components. Power is like brightness, so we're really talking about which circuit or which light bulbs which be brighter or dimmer and so forth. So take a moment and jot down your answers about the brightness and how it changes initially to finally for A, B, C, and D, and for the entire circuit. Okay, so to help you through your reasoning on this, hopefully you were thinking of the power equation, P equals I squared times R, or V squared over R, or I times V, in leading you to get those answers. So, looking at the entire circuit, we know that the total resistance has decreased, R, yet the voltage of the battery stays the same, the EMF. And so as R has decreased, this has caused the total power to go up. So the whole circuit will get brighter if you add another circuit element into here. That should make sense. You're adding another device into it, so you're using more power. Now, what happens to the brightness of the bulbs? Bulb A should get brighter. Why? Because the current through it has increased, and power equals I squared times R. R is constant, and so as I goes up, the power goes up, so brightness of bulb A gets brighter. And then B will definitely get brighter because it was not lit at all. There's no current flowing through it, and suddenly now there's current going through it, so B will get brighter. C and D, on the other hand, will become dimmer. And that's because the voltage across them is less, and the current is less through them. And so the power, which is equal to I squared times R, you have a smaller current for the same resistance, and since they get dimmer. And there, summarize, the power here increases for the whole circuit because power equals the EMF divided by, or EMF squared divided by the resistance. And the total resistance has decreased, causing an increase in the total power. And for A and B, power equals I squared times R. We can use that formula. The resistances are staying the same, so the current has increased, which has increased the power, making them brighter, the bulbs. And for C and D, you can use the same formula. Power equals I squared times R. But in this case, the current is decreasing, causing a decrease in power, hence making them dimmer. I'm sure there's multiple ways of explaining this question. This is just one way that I go through in class typically. You also could talk about power equals current times voltage and describe it that way. So hopefully this gives you an idea of how to solve conceptual questions that typically come up in the multiple choice section of the exam. Okay, and that's it for this example.